In this problem, it's kind of interesting because we have the graphs of the first and second derivatives. We're not told which, so we're supposed to figure it out on our own, and then we're supposed to draw the graph of f. So I'm looking at these. I know that one of them is the derivative of the other. So if I look at this, maybe this is f prime, but if it were, then it's got a level spot here. So the red one would have to be its derivative. Its derivative would have to be 0 there. So that's not going to work. So whereas if I look at the red one, the derivative of the red one, if that was f prime, then the derivative here would be 0, and lo and behold, the blue one is crossing through 0 right there, right? In fact, the red one's increasing here, and the blue one is positive. The red one's decreasing here, and the blue one is negative. So it fits better if this is f prime and this one is f double prime. It just doesn't work the other way because the level spot. So here, if the red were the derivative of the blue, then there's a level spot here. It would have to be crossing through the x-axis. Okay, so first part's determined. I know which one is the first derivative and which one is the second derivative. So when I look at this, the first derivative is positive all the way, which means no matter what, f prime is greater than 0. That means the function is always increasing. That's good to know. All right, and the other thing I see, I can tell about the concavity of this function. Over on this side, f double prime is greater than 0, but over here, f double prime is less than 0. That means over on this side, the function is concave up. Over here, the derivative is still positive, right? But it's now concave down because the second derivative is negative. Okay, we can also see that the graph has maximum steepness right here. So then as we go along, then the steepness decreases. As we go back, then the steepness decreases. The graph seems to be slowing down in its growth, right? It looks like that's going to 0. And it's straightening out because the second derivative is going to 0 as well. So we're losing our concavity. The concavity is going towards 0. So if I want to draw the graph of the actual function, so one thing I can't do is decide how high the function is. If you had the function and you shifted it up, that wouldn't change the slope profile. But so I'll just maybe say, suppose that that the function is such that at 0 it goes through this point, just so I have a starting point. I can see the function has its maximum steepness here, a slope of about 1. So let's see, according to this scale, a slope of about 1 would look like this. So it's got a slope of about 1 here. As we go forward, the graph is concave down but increasing. So something like this. And as we go backward, the graph is concave up. But the slopes are still positive, so something like that. So from the two, the first derivative tells us the direction the graph is moving and gives us a sense of what the slopes are. The second derivative tells us about the concavity. From those two, then I get a pretty good idea of what the actual function f might look like. And notice, as I said before, if I were to shift that function up, maybe so as here, shifting it up or down wouldn't change the first derivative. If the first derivative doesn't change, then the second derivative would stay the same as well. So we can't really locate where this graph is vertically unless we had some information about maybe a starting point or a particular value of the actual function. In this case, all we were given was the first derivative and second derivative, so we did what we could do.